Hi everyone, this video is the solution to example 1 of plastic section properties. The idea in this video is to solve the elastic section properties and the plastic section properties for this rectangular section with base 300 and base 400, but we're also going to try to solve it in a more generic way for a base B and a height h. The first thing we're going to calculate is the elastic section properties, and basically the elastic behavior of this section assumes a certain stress distribution. So for a given M, imagine an M that causes compression on the top and tension on the bottom, the stress distribution is linear. So something that looks like this will be the stress. And the equation is given by stress equals M divided by Ixx times Y. And it's this Y term, being Y the distance to the centroid, so let's write it here. This is Y. It's this Y term that gives you this linear distribution. But to calculate the elastic section properties in terms of the section on its own, the only thing we need to get is this elastic section modulus, which is going to be equal to Ixx divided by Y max. So what's the idea here? If you take this equation here, we can write this equation as M divided by the elastic section modulus if we define the elastic section modulus as Ixx divided by Y max. So this quantity, the elastic section modulus, will help us define the elastic behavior of the section. And now, why is it Y max and not just Y? Because now we are actually writing this same equation on the top, but to find sigma max, so to find the maximum stress in the section. So if you're interested in finding this value here, either this top one or this bottom one, let's call this sigma max, and there is also sigma max. To do that, we need to substitute y with the coordinate of that fiber, so we substitute it with y max. So with that in mind, we can now calculate both of these quantities. So Ixx is nothing more than bh cubed over 12. In this case, if we substitute b with 300 and h with 400, we get that this is equal to 1600 times 10 to the 6, and the units for this is millimeters to the power of 4. Y max is just the coordinate of the top or the bottom fiber, is nothing more than h over 2. So in this case, it will be 400 divided by 2, so it's 200 millimeters. Which means that for this section, the elastic section modulus is the 1600 times 10 to the 6 divided by 200, which should give you 8 times 10 to the 6 millimeters to the power of 3. Now, if you want to solve this for a generic case, the elastic section modulus is nothing more than bh cubed over 12, so that's Ixx, divided by h over 2, because that's Y max. And this is equal to bh squared over 6, which should still give you square millimeters, or depending on the units of b and h. And if you substitute b with 300 and h with 400, you should get the same answer as here on top. So this gives us the behavior in the elastic stage of the section. So everything is linear and stress is proportional to the moment. But we can now calculate something very interesting, which is the elastic resistance of the section. And the elastic resistance is nothing more than taking this equation of sigma equals m divided by w elastic and just replacing sigma, so the maximum stress, with Fy being the yield stress of the material. So if we do that, we can say that the elastic RD, so let's do like this, MRD elastic, so the resisting moment in the elastic stage is nothing more than Fy times the elastic section modulus. And this gives us the moment that a given section can resist in the elastic range. In this particular case, we know that the elastic section modulus is 8 times 10 to the 6. If we multiply this by Fy, whatever Fy is, we can get the resisting moments in the elastic range. Now, once we get to this moment, so once we get to the elastic resistance moment, we still have capacity of the section. And why that is? Because once we get to that moment, the only thing we calculated is to say that this sigma max on the top and on the bottom reach Fy. So they reach the yield capacity of the material. But what that basically means is that the top fiber, so if you think about here, the first fiber of the section here in green, and the bottom fiber of the section, so the last fiber, these fibers will plastify, but the rest of the section is still good, right? It still can resist load. So that means the moment can still increase. That means the real resistance of the section is larger than the one we just calculate. So what this video is all about is calculating the plastic section properties. And the idea behind the plastic section properties is we still consider our original section, our original rectangle, but now at a certain moment the entire section will plastify. And this will happen since this is symmetric. The top part will plastify under compression and the bottom part will plastify under tension. So if you guys think about the stress diagram in this case, is the top part will have a constant stress of Fy and the bottom part will have a constant stress of Fy. So both of these values, here is Fy and there is also Fy. So only when we get to this stage, we are going to get the entire section plastifying, and only here we're going to find the real final ultimate resistance of the section. So how do we calculate this? For this we need to calculate the plastic section modulus, and this is done by integrating these forces. So the compression force here, let's call this one Fc, and the integration of the tension forces here, let's call this Ft. What is the value of Fc? Fc is nothing more than Fy times the area of this green space here. So if you think about it in this case, and let's put the dimensions here, if this is 400, this is 300, the Fc is nothing more than Fy times the area. So the area is 200 times 300. And now the only thing we need to do is multiply this Fc by the distance to the plastic centroid. So this distance here, let's call it dc. We multiply this to get the moment caused by that force Fc. So that will be 100. So it's 200 divided by 2, so it's 100. And now if you do the same for the other force, so if you add now Ft, Ft is going to be Fy times also 200 times 300 and also times 100. And if you add all of this up, this gives you the plastic section modulus of the section. So this will be equal to 12 times 10 to the 6 and also times Fy. Now, since we're multiplying this by Fy, we're not calculating the plastic section modulus actually. We're calculating the moment resistance in the plastic range. So if we stop here and rewrite the equation, the moment resistance in the plastic range is equal to the plastic section modulus times Fy. So that means the plastic section modulus is this 12 times 10 to the 6. Now, if you want to generalize this with B and H, it's the same logic, but now we're going to split the section in two as well. So this will be the part in tension, this will be the part in compression, and now our WPL will be, so this is B, this is H over 2, so it will be 2 times, and now we know that both of them will be the same, and then B times H over 2, and then times H over 4. And if you take this into consideration, we get that this is BH squared divided by 4. And the units of this will be millimeters cubed, again, if we use millimeters. So again, if we use this expression with the dimensions 300 and 400, we should get this 12 times 10 to the 6. And that's basically it. What this question actually asks is something that is called the shape factor. So the shape factor about the horizontal and vertical axis. So I'm just going to do the horizontal because the vertical is basically the same. But the shape factor of a section is nothing more than the resistance of the plastic section divided by the elastic section. And since these both are nothing more than WPL times Fy and WEL times Fy, it's just the ratios between the section modulus. So for every rectangular section, since we now have a generic expression, the plastic is BH squared divided by 4, while the elastic is BH squared divided by 6. So the shape factor is always 1.5. What this basically means is that plastic resistance of a section is 50% larger than the elastic section for every single rectangle. So if you do this in the y direction, the same problem now, if you solve it in the y direction, your shape factor needs to be 1.5 because 1.5 is valid for every single rectangle, okay? No matter the dimensions. I think that's all. I hope you enjoyed the video. Thank you for watching and have a nice day.